Hey, today I wanted to talk to you about buffers. What is a buffer and why do we need it? It seems like every circuit I build has at least one of these things in it, usually like this with an op-amp. I have some voltage coming in, it runs into the positive, the non-inverting input of the op-amp, and we have negative feedback, and so on the outside, on the output, we get basically a copy of that same voltage. But that seems rather silly. Why are we just copying the voltage? Okay, let's take a look at my breadboard here. Let's see, of course when I measure here, we get 0 volts. I hope you can see my meter over there. And what do we have going in? We have a power supply of 12 volts, 12.02, pretty close. And what we've got right here is a voltage divider. I'm using these high precision resistors that I got from a bulk package. They're 9.09 kilo ohms each. And so right in between here, we have just about 6 volts, 6.012. Now, that's fine, but what happens if I try to use that for something? Let's say I'll put this wire in here to take that signal and run it through some load. I have another one of those resistors there. So now I'm taking that voltage here and running it through into this resistor here, which is putting some load onto the negative rail though. So now what do we measure here? Now we only measure 4 volts, right? So we've completely destroyed that input signal. So what a buffer does is it allows us to keep the same voltage but amplify the current. So we have 6 volts here with this buffer. How much is going into this op-amp? 0.00 amps. This is an ideal simulation. And what do we have coming out? On this other side, we have almost 600 microamps going through there to ground. In our circuit with the load, right, we have a huge amount of current going through both of these resistors. It's really just 2 resistors in parallel, so it pulls this way down. So what can we do? If we use a single transistor, transistors have some beta value. The beta value is basically the ratio between the input current and the output current. And in most simulations and most textbooks, you'll have a beta value of about 100, meaning that the current coming into the base is 100 times smaller than the current coming out of the emitter, or roughly equivalently, the current coming in through the collector. And so what we see here is only 5.6 microamps going in, right? And about 100 times that, 600, almost 568 microamps going through. And so the resulting voltage drop over here is really small. Let's see that on the breadboard. Okay, so now I have my 6 volt signal coming in here to this base of the transistor, and we see it reading 6.018 volts. It's hardly dropped at all. And on the emitter, right, we have our 12 volt rail, and coming out the backside of this transistor, we have 5.42 volts. And so there's some drop here, right? It's from 6 volts to about 5.4 volts. That roughly 0.6 volt drop is the drop across that transistor. Now, and we see some small drop here. So if I let's measure it over here. You can really see it. Okay, right now it's 6.018, and then if I remove the load, 6.012. Well, not what I was expecting. Add the load. Well, I guess it really makes very little difference. Okay, let's move on to this other pair of transistors here. Okay, so over here I have what's called a Darlington pair. Let's see if I can get you to see that better. Okay, so what we have in a Darlington configuration is that we have a common collector. So you see these 2 pins here are both connected together, and these are both going to our positive rail. So 12 volts. And then in here, this is where we bring in the voltage from our current divider, and then that comes out through this leg here, right? So we have a very small drop there, 6.012 to 6.006. A tiny little drop across that because this diode's not doing very much work, which goes into the base of the next transistor and comes out here. So we've gone through 2 transistors and now we have a 5.4 volt output. So slightly lower, but the drop that we have here, right, is basically negligible. Okay, let's see what the simulation results look like so that we can see that in kind of a really precise way. I know you can't read these numbers that are on the plot, but this is the simulation results. But coming in here to this base, the amount of current that we're sucking off of this voltage divider is only 49 nanoamps. Tiny, tiny little bit of current, right? And then that gets amplified here. The current gets amplified, not the voltage, right? And here we have 5 nanoamps. Right, so just a tiny, sorry, microamps, excuse me, that makes more sense. 50 nanoamps, 5 microamps, right, and up to 500 microamps on the backside. So we can drive 500 amps here by only using 50 nanoamps over here. So that's the advantage of this Darlington configuration. It has a very, very high impedance, right? We can think of impedance as the amount of voltage drop, caused by the current. Okay, and then of course we can implement the same thing with an OpAmp. And so here, this tiny little yellow thing in there is our negative feedback, right? So we're coming from the output back to the negative feedback, and then in this positive feedback, or the non-inverting input, we should say, we have our 6 volts. And so we can measure that input voltage, 6.013, and then the output voltage is here, 6.013. So that OpAmp is doing a great job of copying that without making any impact on that input voltage. So why do we care if we're using transistors or an OpAmp? Well, part of it is a little bit of cost. A transistor costs about 11 cents each when you buy them in bulk, and this is a really cheap OpAmp, and it's about 45 cents or so each. And so it's definitely cheaper to have a transistor than an operational amplifier. We are kind of talking about pennies, but it adds up a bit because in every stage of the synthesizer, we're going to need to do this buffering several times, and so it starts adding up some cost. But that's not the main issue for me, really. One of the big issues that I really try to think about a lot is repairability. Now, if you think about, you've put some components into a proto board. If you want to take it out and repair it, how are you going to get those out? Well, you're going to desolder them. Unless you have a really nice desoldering pump, it's pretty tricky to get these out if you have more than 3 legs. When you only have 2 legs, it's actually pretty simple. I mean, you can just use a rheostat, clip it onto one of the legs, and then when you heat up just one of those legs with your most standard chisel tip soldering iron, and it should just, pop out. You can move the rheostat carefully, don't break the legs, over to the other side, and then gravity should just help this guy out. There we go. Right. So a 2-leg component, super easy to remove. What about a 3-legged component like a transistor? These are a little bit more difficult, but we can put the rheostat across all 3 legs. And then if we heat up all of these pads, kind of work it back and forth, we can get the component out. Just clean that up a little bit. There we go. And we'll be able to use that again. Now if you have an OpAmp soldered in there, it's going to be nearly impossible to get all 8 of those legs off simultaneously. you really need to either have a really good solder sucker using some braid. It's going to take you a while. Or you're going to need a hot air or something to heat up all 8 of those legs simultaneously. So, of course, what you do is you put it into a socket. And if you have a socket soldered in there, that's fine. I mean, your socket's never going to go bad. And then you can just, pop your OpAmp in and out. But a socket actually costs almost twice as much as an OpAmp. So that's the important thing. Thinking about repairability, cost, and also manufacturing. I mean, each joint that you have to solder is another piece of work you need to do. If you can get by with 3 legs on a BJT instead of 4 legs on one of these OpAmp packages, so you get 2 on each 8-pin dip. Just something to think about. Also, more legs means more space on the protoboard, or more space on the PCB in the final design. Anyway, I hope that was interesting. There's something I didn't really address in this video, which is that voltage drop that we get when we use a BJT. Is that a problem?